Hey everybody, today we're going to practice some basic Python skills using the Jupyter programming environment. And we're going to simulate the growth of rabbit populations. And just to give you a quick preview of where we're headed, I'm going to show you several iterations of a small program that calculates populations of rabbits. And I'm going to show you how it evolves. And I am doing this in the Jupyter programming environment. This happens to be an online version called Jupyter Lite. And a Jupyter notebook is basically just a small collection of programs with like intervening text that explain how the programs work. And it's kind of an interactive environment, as you'll soon see. My audience for this presentation is mostly intended to be beginning to intermediate computer programmers. Maybe if you actually know nothing about computer programming, you might at least still kind of get the gist. I think that would be fun if you did, and if you were able to at least follow along, maybe pausing the video a couple times, please say something in the comments. And I think even advanced programmers, might be able to relate to my process and maybe also add some helpful questions or challenges in the YouTube comments. I do intend this to be the first of a series of future videos, and I'll talk about my plans for future videos at the end of this presentation. But let's just get started and start talking about rabbits. So we're going to start with a single female rabbit whose name is Daisy, and we're going to assume that Daisy never dies. We're going to assume that her daughters actually never die, and we're going to assume, at least for the first program, that Daisy is the only rabbit, the only mama rabbit, and that she reproduces once a month. Because Daisy is the only mama rabbit, her daughters actually never reproduce in the first couple versions of the program. And last but not least, there's kind of an implicit assumption here that I don't really care about the male rabbits. I just kind of assume that there's an equal number of males and females, and that the female rabbits or in this case just Daisy, are always able to find a male to breed with in order to have the offspring. So we will model rabbit populations in terms of females, and then any conclusions we draw from that we can pretty easily extrapolate to both males and females. But with no further ado, let's look at the first program. So you can see this. Let's see, this is about a 8-line Python program, including the comment. And it's a pretty simple setup. So I have my original rabbit, the OG mama is going to be named Daisy. She's going to be the grandmama, then the great-grandmama. She's like the Eve of this like little Garden of Eden of rabbits. I'm going to keep track of the rabbits, the total population of rabbits in a Python list called rabbits, which starts with just Daisy. And then I'm going to have a loop, and that loop is going to, for starters, I'm just going to loop through 5 generations of rabbits, and then in each month of rabbit reproduction, I'm going to print out what the month is. I'm going to print out what the population of the rabbits is, and then this is by far the most important statement of the program, at least in terms of what makes it interesting, is that I'm going to extend the population of rabbits by simulating Daisy having a daughter in the month M. So let's just run it. Let's run it. It's kind of a pet peeve of mine when I see other people try to explain their programs. They spend all this time explaining their program, and then sometimes all you need to do is run it, and then you can kind of get the gist of it. And then once you see it, hopefully you can then kind of go back and make sense of it. So anyway, the output, and by the way, this is a nice feature of Jupyter, is that all I did to run the program was I hit the play button, and then it produced the output of the program. And as I kind of mentioned before, there are 5 loops through the program. During each loop, I print out what the month is. So here's the code that says print month M. And you can see every other line is month 1, month 2, month 3, month 4. And you can see that the rabbit population is growing just by virtue of Daisy being a mama rabbit that has a new rabbit every month. So I'll let you maybe pause and just kind of read this if you're not totally getting the gist while I take a little sip of my coffee. And then, as I said earlier, like the point of this exercise isn't necessarily to get to like the most elegant or concise version of the program immediately. I want to show you how like a real sort of thought process works and how you can incrementally improve your program just by kind of asking yourself questions. So the first question that I kind of asked myself as I was developing these small programs is like, how can I make a simple improvement to our program so far? I'm pretty happy with my first version of the program insofar as it gets me started thinking about the problem and it seems to produce sensible output. But I want to make it more obvious how I generate the names of the rabbits. Like when I make this little statement here to extend the rabbit population with the daughter of Daisy, the naming mechanism isn't really very well encapsulated. So in the second version of the program, all the only real substantive, that's a hard word to say, substantive change is that I added this baby function. And so now when I extend the rabbit population in the main loop of the program, I delegate the actual details of coming up with the baby name to the function, to this baby function up here. And I violated my own principles by explaining the program in excruciating detail before I actually let it run. Although I think in this case, maybe I was appropriate to do that because I haven't actually changed the behavior of the program. This is what you might call a refactor in the program, where the program has the exact same behavior. I've just kind of cleaned up the internals of the program. So then, as I made this Jupyter notebook, I added like kind of notes and questions to you, questions to myself, and one note here, and I didn't even realize this as I was doing it, is that my baby function is actually not really just like a simple inlining of this. I actually made it more general. And so I would maybe pause the video now, if I can get it all on the same screen, and ask yourself, why is this baby function actually more versatile than this statement here? And the answer is that I've actually parameterized my baby function not only on the month, but on the mother's name. So I am no longer making the assumption that Daisy's going to be the only rabbit. Now, it just so happens that in this particular instance of the program, Daisy will be the only mama. But I've actually set myself up for future improvements by making the name of the baby be parameterized not only by the month, but by the name of the mother. And we'll see that soon. And that change actually led to a perfect segue for me to extend the rabbit biology model. And whoops, sorry, I didn't mean to go into edit mode there. So new assumptions about rabbit biology. We're now going to allow for the possibility that Daisy's daughters and granddaughters and great-granddaughters and so on, and basically all of Daisy's descendant female rabbits can reproduce. And we're going to say that every female rabbit actually does reproduce every month, every cycle. And we're going to say that all the other assumptions from the prior program stay the same. In other words, like no rabbits ever die, which I know is unrealistic, but I do like rabbits, so I would love to live in a world where rabbits at least died less. I wouldn't want to live in a world with infinite rabbits. But, and then we ignore the males because we know that whatever we discover about the females, we can pretty safely extrapolate that to a population that also includes males. And it's just simpler if we just think in terms of the females. So here's a little thought question. Take my word that the next version of my program is going to incorporate these new assumptions about rabbit biology. Um, when we saw Daisy just producing daughters, the number of rabbits every month only increased by one. So basically, if you wanted to know how many rabbits there were in month, extrapolating from this, if I told you we're like in month 63 and I asked you how many rabbits there were, you would say, well, there were 63 because Daisy had a daughter every month, and that's pretty simple math. You count it on your fingers for the first 10 months. But in this new paradigm where we have these new assumptions about rabbit biology that the daughters reproduce every month, why don't you pause the video and maybe even if you need to, try to read this program and try to make a guess about how many rabbits there actually would be. So it turns out that with this new paradigm, you actually get 2 to the n rabbits every month. So it basically doubles every month. We start with Daisy, then we get Daisy and her daughter, then we get Daisy and her daughter from the first month, her daughter from the second month, and then her first granddaughter, which is the daughter born in month 2 to the daughter born in month 1 to Daisy. And then the numbers continue to double to 8 to 16, 32 to 64. And you can start to see that my way of naming rabbits is just getting like incredibly clunky and onerous and kind of absurd. So like, let me see if I can properly select one of these. So one of the rabbits in our population after how many months is it? In month 7. By the way, I sort of increased the number of months without calling it out. But there's in month 7, you have a daughter born in month 6 to a daughter born in month 5 to a daughter born in month 4 to a daughter born in month 3 to a daughter born in month 1 to Daisy. So she is Daisy's great great granddaughter. I mean, I'm sure I'm off by one in describing it. But my more important point here, I think, is that if I just like gave you this array of rabbits and said, hey, here's the population from month 7 that I simulated, and you tried to draw any conclusions about this other than that there's 64 rabbits, it would be fairly difficult, I think, for you to like really make sense of this program. I think the first couple rabbits in the list, in the Python list, maybe convince you kind of the basic mechanism here, which is that, you know, once you have daughters having daughters having daughters having daughters, that it would make sense that it would be some sort of exponential function. You know, maybe you wouldn't predict exactly 2 to the n, but you would probably assume some sort of exponential function going on. So anyway, I have this observation. This is a really bad pun, and I apologize for this. The population of rabbits doesn't just grow rapidly, it grows rapidly. And then I also stated our problem that the representation of each rabbit is incredibly verbose and kind of opaque. Maybe opaque's the wrong word, but unwieldy. And then that kind of led me to my next step, which is I want to remove some noisiness from our program. So in order to remove the noisiness from the program, I stopped naming Daisy. She's just now rabbit 0. And I stopped having these like long sort of English sentences for the names of the rabbit where I say daughter born in month blah blah blah. And excuse me, all I do in this case is I just append the month that the rabbit was born to the name of the mama rabbit, and that becomes the name of the baby rabbit. And you can see that here probably more clearly than from the program itself. So we start with Daisy, rabbit 0. I'll continue to call her Daisy probably, but Daisy is now just named rabbit 0. Her first daughter is named rabbit 0-1. Her second daughter is named 0-2. And then her granddaughter, which in our old parlance would be the daughter of the daughter born in month 1, who was the daughter born in month 0. But the granddaughter is 0-1-2, and so on and so forth. So you can see that our naming scheme is definitely more concise than before, but it's still kind of clunky and cryptic. And kind of the whole paradigm of this presentation is that when you're developing software, you're always kind of asking questions to yourself. And in this presentation, I'm kind of relaying those questions to you. So I asked a question, like, does our new naming scheme, albeit clunky, does at least have the property that names are unique for each rabbit? And if you look at when we have 64 rabbits in month 7, take a moment to pause the video here and see if you believe my assertion. And by the way, I kind of gave away the answer here because I didn't have this scrolled off the screen. But the answer is, in fact, yes. I can assert with 99.99% confidence that you get unique rabbit names. And you can kind of do a basic inductive proof. And I think this is something that most people learn in high school algebra, but you probably have forgotten. But there's this basic mechanism for doing inductive proof that if you can prove the base case of something and then you can prove the induction step, then you can basically prove that some result holds for an infinite value of integers. So you basically prove that something works for n equals 1, and then you prove that if you can assume something works for n, then it'll work for n plus 1. And as that general proof scheme pertains to our problem of unique rabbit names, the inductive proof will be, for the basic case, we're just going to examine the output, really, and just look at the first few generations of rabbit. And then for the induction step, we'll think about names during each new generation of rabbits. So for the base case, all I have to do is just if I look at, I probably technically only need to look at month 1 for this proof to work, but I can very quickly examine the first 3 months and convince myself that, okay, obviously in month 1, there was only 1 rabbit, so there's no worry of duplicates. Month 2, there are clearly no duplicates. Excuse me. And month 3, but by the time I get down to month 7, I don't want to keep scanning the output, and that's where the induction step comes. So the induction step for rabbit names, my proof logic is that you start with the idea that in month n plus 1, all the mamas from month n have different names from each other, and that's by the inductive step. I don't have to prove that for this part of the proof. And then I notice that all the new babies have the new month-based suffix. So all of these babies toward the end of month 6 have that little -6 on the end of their names. All the new babies have unique mothers, because I said every mama rabbit only has 1 daughter per generation. And then all the new babies have unique names based off their mother. And therefore I conclude in generation n plus 1, all the rabbits have distinct names. So then this question wasn't really to myself. This question is actually to you, the viewer. Does the above proof convince you? And I would posit that you might say no, maybe not. But maybe I can further convince you, and actually I can further convince myself, so we can further convince ourselves by having actually the program verify that the unique names, that the names of the rabbits are in fact unique, that there are no duplicate names among the rabbits. And then this sets up an implementation question, which is how do you tell if a Python list of items has all distinct items? In other words, that a list has no duplicates. And I'm going to have a sip of coffee while you maybe ponder that, and maybe you're lucky enough to actually know this idiom already. And we'll get to it obviously soon. And then a final question is why do we even care if the rabbits have different names? We're going through all this trouble to give every rabbit a distinct name. I've like worked myself, or I've worked up a mathematical proof based on induction from ancient high school math principles to prove that they're unique. And it's like, really my long-term intention is just to count the number of rabbits. So I don't need to like give every rabbit a unique name. I'd need to probably just, keep some sort of counts and bucket all the rabbits from the same generation together. But having said that, I'm gonna run with it. I'm gonna see. I'm just gonna go with our current assumptions. Go with my current implementation. Convince myself that my current implementation is sound, and then from there, we'll see where this goes. We're getting to the end of this video, by the way. This is the last step, if I recall correctly. Yep. So in my last version of the program, I'm going to answer the question I posed to you, which is how do you make sure the rabbit names are unique? And what I do here in Python is that I assert that the length of the rabbits list is the same length as the set that I would get by sending the rabbits function to the set function. And a quick review on how sets work in Python, I think will sort of illustrate why I chose that strategy and why I think it's sound. So if I print a set of numbers that are distinct, like 1, 2, 3, 4, 5, if I initialize that set from an array of distinct numbers, that set has the same number of elements as the array. And note that sets are denoted with these, it's kind of hard to see probably on the video, but these are like little squiggly brackets as opposed to the square brackets of a list. Whereas the set of numbers, the set based on a list of numbers that has a lot of duplicates ends up having a shorter length than the original set. And hopefully that's clear. But going back to this program, I didn't actually show you running it. And it turns out when you have an assert statement in Python, like if the assertions are succeeding, they succeed silently. So it's like not totally clear that they're running. So in order to assure you that like this assert statement is actually doing something, I'm going to just like temporarily break it. Like let's say that I thought that the way that you detect duplicates somehow involved like adding 37 to the length of the set, which would be pretty absurd. Then if I ran this program, I would get this assertion error that told me my logic was clearly wrong. So I'm going to undo that, run it again. And now we get just the same output as before, and the assertions silently succeed. And I want to be clear here that this assertion doesn't prove to me that the rabbits are exponential, that every month rabbits has 2 to the n. Every month has 2 to the n rabbits, but it gives me a lot more. Well, actually, this is not asserting the number of rabbits, but that that during every month I have uniquely named rabbits. This doesn't prove it forever, but it gives me a lot of confidence that my original mathematical argument up here, where I did the induction step, that argument is probably sound, and I haven't overlooked any obvious details. So that's going to wrap it up for this video. I want to talk a little bit about goals for future videos. I hope that if you enjoy this, that you add some comments to the video, maybe suggest things that were confusing to you or that you would want to go deeper on. But I do have some more ideas already that I intend to follow up on. And the meat of the idea is that I want to use a more interesting simulation of rabbit growth. And I kind of wish I had mentioned the Fibonacci sequence a little bit earlier in this presentation, but the classic Fibonacci sequence that you learn in high school, where you have the numbers like 1 + 1 = 2, 1 + 2 = 3, 2 + 3 = 5, 3 + 5 = 8, 5 + 8 = 13, 8 + 13 = 21, and so forth. That sequence was actually popularized by Fibonacci in terms of explaining an idealized rabbit population. So I'm going to go a little deeper on that. And I think you'll find that I can go a little deeper on that problem than just the surface. of it and find some interesting things. And of course, we'll continue to improve our existing program, and we'll try to gain some mathematical insight into the population model, and maybe we'll even make some charts and start to take advantage of some of the nice features that you get from this Jupyter notebook. But anyway, thanks for listening, and have a great day.